Hi, I'm Xiangming, and here's my final project for computational photography. And my subject is fast separation of direct and global components of a scene using high-frequency illumination. And firstly, let's define what are the direct and global components of the scene. So the radiance of a surface point measured by the camera pixel due to the significant scattering events is referred to as the direct component of the scene. And the remaining radiance measured by the camera pixel is referred to as the global component. Well, in addition to the interreflections, the global illumination received by the camera pixel may due to volumetric scattering, subsurface scattering, or even light diffusion due to the translucent surfaces. So the separation of the direct and global components of measured radiance is useful as those components convey very different properties of the scene. Direct and global components at all scene points can be measured by using high-frequency illumination patterns. When the light source radiates a high-frequency illumination pattern, the lit pitches include both the direct and global components of the scene. Well, unlit pitches have only a global component. Let us divide the surface into a total of n pitches, m of which are directly visible to the light source. We denote the radiance of the pitch I measured by the camera C as LCI, and its two components as LD and LG. Well, LIG is the radiance of pitch J in the direction of pitch I, and AIG incorporates the BRDF of I, as well as the geometric configuration of the two pitches. We can further decompose LG into two components as LGD and LGG, where the LGD is due to the direct component of the radiance from all scene pitches, and LGG is due to the global components of radiance from all scene pitches. Well, let us assume that only a fraction of the scene pixels are activated, and those activated pixels are well distributed over the entire scene to produce a high-frequency illumination pattern. The set of illuminated pitches can be denoted as Q, where the function lit indicates whether a pitch is illuminated or not. Then the above components can become the following equations. And finally, we compute the direct and global components of scene using the maximal and minimal brightness values at each camera pixel. Here's my experiment setup. I use the projector to create a high-frequency illumination on scene, and I use the camera to capture the scene images. I used the checkerboard pattern with sets of 8 by 8 pixels in the projector, and I shifted the pattern 6 times by 3 pixels each time, and captured a total of 36 images. After capturing the images, we compute the maximum and minimum brightness values of each pixel, and with them, we can compute the direct and global components of the scene. I captured a set of scenes that are dominated by a specific physical phenomenon, like subsurface scattering, as we can see here. And we notice that the appearance of the snub toys and grips is dominated by the subsurface scattering, as we can see from the global image. And as for the translucency, the global image mainly contains refraction and caustic effects due to transparent objects. It also shows volumetric scattering in the glass cup. This separation method can be achieved by using a line occluder, such as a stick that's swiping across the scene to create a high-frequency shadows. And finally, with the direct and global images computed from separation, we can adjust the weight of direct and global components to form a novel image. Thank you for watching.